how to move from the boring world of flatland with the Lewis structure to the exciting world of 3D dimension with VSEPR. We are going to see this in this video. So let's put our 3D eyeglasses and let's go into the 3D world. Let's start. So VSEPR is an acronym which stands for Valence Shell Electron Pair Repulsion. The first two words, valence shell, are there because this model takes into account only the valence electrons of the central atom, even if central atom is implied in the acronym. So it's not like the Lewis model, because in the Lewis model we were considering the valence electrons of all the atoms we had in the molecule. Now we have to focus only on the central atom. The last three words of the acronym are there to tell us that this model finds the molecular geometry by watching the electrons' repulsion around the central atom. In other words, this model finds the 3D structure of molecules looking to the valence electron pairs of only the central atom and assuming that those pairs, since they are negatively charged, they will repel each other, and so they will tend to space themselves out as far apart as possible because of this repulsion. Therefore, repulsion between these valence pairs of electrons determine the shape of the molecule. This is the concept of VSEPR model. Let's take an example. If we have two electrons pairs around a central atom, regardless if these pairs are bond pair or lone pair, at this stage of this video, these two electron pairs will repel each other because they are both negatively charged. So they will tend to space themselves out as far apart as possible. So the only way they can do that is to place themselves at 180 degrees. As you can see now, the shape of this electron arrangement is linear. Now, depending on the number of valence electron pairs we have around the central atom, we can have several kinds of electron disposition. For instance, this table summarizes all the cases starting from 2 valence pairs till 7 valence pairs. So, as we have already said, with 2 electron pairs around the central atom, the electron arrangement is linear. On the other hand, if we have 3 valence pairs around the central atom, this time the electrons will place each other at 120 degrees away one from each other. And so the electron arrangement is called trigonal planar. 4 pairs of electrons will locate at 109.5 degrees apart, giving rise to what is known as tetrahedron. 5 valence pairs will give rise to the so-called trigonal bipyramid. Now, it's important to note that starting from 5 electron pairs around the central atom, now there are 2 different kinds of position. In particular, we have equatorial position, which are the 3 pairs of electrons in the plane position, and they are at 120 degrees apart one from each other. And then we have also the axial position. These 2 electron pairs, they form an angle of 180 degrees between each other. On the other hand, the angle with the electron pairs in equatorial position is 90 degrees. So with 6 electron pairs around the central atom, we have the so-called octahedron electron arrangement. Also, octahedron has equatorial and also axial position. On the other hand, octahedron is more symmetrical if compared with trigonal bipyramid, because octahedron has all the angles which are 90 degrees. However, in the case of 7 electron pairs around the central atom, more than one electron arrangement are possible, as you can see from the table. So far in this video we have considered the electron pairs in general. However, as you may know, electron pairs can be divided into two categories. Lone pair, which are the electrons that the central atom doesn't share with other atoms, and then we have bonding pairs of electrons. The bonding pairs of electrons are shared between the central atom and an external atom. In VSEPR model, the lone pair are considered more spatially expanded around the central atom. So this model tells us that the lone pair, since they only feel the attraction with one nucleus, which is the nucleus of the central atom, then lone pair are bigger if compared with bond pair. Bond pair are affected by the nuclear charge of two nuclei. So since they are shared, they are considered smaller around the central atom, since they also extend themselves near to the second atom. This difference between lone pair and bond pairs can also be seen in the different electron density near the valence core. In particular, lone pairs contributes with two net negative charges around the central atom, whereas bond pairs, which are shared between two nuclei, provide a net electron density which is less than 2 electrons. So, lone pair provides more electron density around the central atom, whereas bond pair provides less electron density around the central atom. This means also that lone pair are more repulsive than bond pair around the central atom. For these reasons, VSEPR model tells us that there is this order of repulsion to take into account. The repulsion between one lone pair and another lone pair is greater if compared with the repulsion between one lone pair and one bond pair around the central atom. And this last repulsion is greater if compared with the repulsion between only one bond pairs and another bond pairs around the central atom. So this is the order of repulsion we have to take into account for this model. Is highly important in order to build our structures. But these repulsions depends also on the angles between the electrons pairs. For instance, we will have the highest repulsion if the two lone pairs will be at 90 degrees one from each other, because the angle is very small. On the other hand, if the angle is greater than 90 degrees, so for instance is 120 degrees, now the repulsion is less if compared with the previous one, and if the angle is even greater than that, so the maximum we can have is 180 degrees, in this case the repulsion between these two lone pairs is of course the least we can have. Same consideration we can do with repulsion between bond pair and lone pair. The maximum repulsion will be at 90 degrees. Less repulsion will be at 120 and the least repulsion will be at 180 degrees. The same considerations we can do also for bond pair repulsions. In summary, if we want to build molecular geometry, we have to take into account the type of repulsion we have in that molecule. If the repulsion is between lone pair, this repulsion is the highest repulsion we have, and the least repulsion we have, it will be between bond pair and bond pair. The second point is that we have also to take into account the angle between those electron pairs. If the angle is 90 degrees, at 90 degrees we will have the highest repulsion between electron pairs. Those are important to define which geometry is more unstable and which geometry is more stable, and so is our molecular geometry. Before seeing how to build the molecular geometry with the VSEPR model, we have to understand the difference between these two words. The word electron arrangement and the word molecular geometry. The electron arrangement indicates the position of the pairs of electrons around the central atom. This property cannot be experimentally determined. On the other hand, the word molecular geometry indicates the position of nuclei around the central atom. This means we do not have to take into account the lone pair when we are defining the molecular geometry. So, when you define the molecular geometry, please erase the lone pair. The molecular geometry is a property that can be experimentally determined. An example of electrons arrangement is in our first table we have seen in this video. What is molecular geometry? We are going now to see it. So, how we can extract molecular geometry with the VSEPR model? To understand that, we will build a flowchart which I have invented for helping you to understand all the steps we have to do to define the molecular geometry with this model. So let's start. First, in order to build the molecular geometry with this model, you have to write the Lewis structure of your molecule. How to write the Lewis structure of your molecule, I have already discussed that in my last video. You can find the link to this video below. So once we have written the Lewis structure of our molecule, we have to count the valence pair of electrons of only the central atom, so just the central atom, in our molecule. So count the valence pairs we have, and also with the help of this equation you can count how many lone pair you have in the molecule and how many bond pair you have there. Once you know the VP number, so the valence pairs number, you can already define the electron arrangements of these electrons following the table I have given to you at the beginning of this video. So for instance, if VP is 4, the electron arrangement is tetrahedral. Now we have to start to see how many lone pairs there are in our molecule. If we have 0 lone pair, in this case the electron arrangement is equal to the molecular geometry and our exercise is already ended. Let's do an example. Let's take CH4, so methane. Let's follow our first rule. Let's write the Lewis structure. Let's count how many valence pair we have there, how many lone pair and how many bond pair. As you can see, we have 4 valence pairs, and all of these 4 valence pairs, they are bond pairs. This means that we have 0 lone pairs in the molecule. So we have now the VP number. Let's take our table, and as you can see from the table, with VP equals to 4, we have the electron arrangement of the tetrahedral. So now, since we have 0 lone pair, as I told you, the electron arrangement equals the molecular geometry. What does it mean? This means that tetrahedron is also the molecular geometry of methane. So the exercise is ended. What happens if in our molecule we have that lone pair is not equal to 0, but is greater than 0 and it's equal to 1? In this case, we have to ask also ourselves another question. Which is the number VP? VP is greater or equal to 5 or is less than 5? Why we have to distinguish between those two possibilities? Because as I told you, when we have 5 or more than 5 electrons around the central atom, now we have shape with less symmetry. And now we have to distinguish between equatorial position and also axial position. So this means we do not know where to place lone pair, if we have to place lone pair in an equatorial position or if we have to place lone pair in axial position in order to build our structure. That's the reason behind this question. So let's see VP. If VP is not greater or equal to 5, this means that Vp is less than 5, then the geometry will be given by the electron arrangement without considering the position of lone pair. So just erase the lone pair and you will have your molecular geometry. Let's do an example. Let's take the most famous example for this situation. Let's take ammonia. So let's write the Lewis structure. Then let's count the electrons. We have 4 Vp, then we have 1 Lp and 3 Bp, 3 bond pair. Once we know Vp, so Vp is 4, let's take our table. Let's see. Again, Vp equals to 4 is the tetrahedral arrangement of electrons. Now, since Lp is equal to 1 and Vp is less than 5, this means that our geometry will be given by the electron arrangement of the tetrahedron minus the lone pair. So just erase the lone pair. What is left is what is called the trigonal pyramidal geometry. Now there is also the question of which are the angles of this trigonal pyramid. Well, since we start from the tetrahedron has, as we know, 109.5 degree of angles. Now we can think that also trigonal pyramid will have 109.5 degree angles. However, this is not completely true, because what is also telling us the VSEPR model is that if there are lone pair on the molecule, that lone pair, since, as we have already said, they are more repulsive, they have more electron density, they are bigger, they will shrink the bond pairs electrons. So what will happen is that the angle of ammonia is not 109.5 degree, but is less than that, and in particular in the case of ammonia is 107 degree. Now let's go back to our flowchart. What happened if in the same case as before, so with one lone pair, now we have Vp which is greater or equal to 5. In this case you will have the problem of where to place lone pair. So you have to place lone pair in the position in which the repulsion between lone pair and bond pair at 90 degree will be minimized. So let's do an example. Let's take SF4 molecule. So let's write the Lewis structure of this molecule. Let's count the Vp and all the electrons pair we have there. You will find that Vp is 5, lone pair is 1, and bond pair is 4. So now with Vp equal to 5, let's take our table about electron arrangement, and you will see that with Vp equals to 5, we have the trigonal bipyramid electron arrangement. So now we can have two possibilities. One is to place the lone pair in axial position, and the other one is to place the lone pair in the equatorial position. Which of these two structure is the most stable one? To see that, let's follow the last rules I give to you. Let's place the lone pair in the position in which the repulsion between lone pair and bond pair at 90 degree will be minimized. So let's see how many repulsion between lone pair and bond pair there are in our first structure with lone pair in axial position. In this case, the repulsion between lone pair and bond pair at 90 degree are 3. Whereas in our second structure, in which the lone pair is in the equatorial position, the repulsion between lone pair and bond pair at 90 degree are only 2. Because this lone pair will repel at 90 degree only with the 2 bond pair in the axial position. So, if you consider only the repulsion at 90 degree, you will discover soon that the most stable structure is our second structure with the lone pair in the equatorial position, because the repulsion at 90 degree are only 2. So now, to define the geometry, again, you have to erase the lone pair. As we always do in VSEPR, you have always to erase the lone pair in order to have the geometry. So what is left if we erase the lone pair? What is left? It's the so-called seesaw molecular geometry, because the shape is like the shape of seesaw. That's the reason why this name. Now let's be back to our flowchart. Let's see the last case. What happens if we have more than 2 lone pairs in our molecule? Again, we have to distinguish between VP less than 5 and VP greater or equal to 5. If VP is less than 5, then we do not have the problem where to place this lone pair, so we can define the geometry as usual only by considering the position of the bond pair. Let's do an example. Let's take the molecule of water. Let's write the Lewis structure of water. Let's count the electrons. VP is 4 with LP equals to 2 and BP equals to 2. So let's take our table. Let's see with VP equals to 4. We have seen that many times in this video. VP equals to 4. The arrangement is tetrahedral electron arrangement. So let's write this electron arrangement for water. Now, we have 2 lone pairs there. But we do not have problem since the geometry is highly symmetric. Since we do not have equatorial or axial positions in this geometry, so in the geometry of the tetrahedron, we do not have the problem where to place these lone pairs, because all the positions are equivalent in this case. So we can simply erase the lone pair and see what is left. So what is left from the tetrahedron if you erase 2 positions, so 2 lone pairs? Is left the so-called bent geometry. So the bent geometry is the molecular geometry of water. Again, what is the angle? Again, you may think the angle is the angle of the tetrahedron, since we start from the tetrahedron to build this molecular shape, but this is not true, because as we have already seen for ammonia, the presence of lone pair, since lone pair are fatter, let's say, they are more repulsive, they will occupy more space around the central atom and they will shrink again the angle of the bond pairs. So, and since now we have also 2 lone pairs, these lone pairs will repel one from each other. So they will try to space themselves out as far apart as possible, because they are both highly repulsive, and then they will also repel more the 2 bond pairs are there. And so this means that the angle for water won't be 109.5 degrees, won't be 107 degrees as for ammonia, but it will be even less than that. And it will be, in the case of water, 104.5 degrees. So let's see the last case. LP greater or equal to 2 with VP greater or equal to 5. Now, in this case, there is the problem where to place this lone pair, in axial position or in equatorial position. And also there is the problem that we have more than 1 lone pair there. So, this means, in this case, in order to find the most stable structure, we have to place the lone pair in the position in which the repulsion between lone pair and lone pair at 90 degrees are minimized, and also the repulsion between lone pair and bond pair at 90 degrees are minimized. Then, once you have found the most stable structure, just erase the lone pair and you will have your molecular geometry. Let's do an example. Let's take SLF3 molecule. Let's write the Lewis structure. Let's count the electrons. VP is 5 with lone pair equals to 2 and bond pair equals to 3. So the electron arrangement for VP equals to 5 is, again, as we have seen many times, is the trigonal bipyramid. So now we have the electron arrangement. But where to place these 2 lone pairs? In this case, if we write the electron arrangement of trigonal bipyramid, you can see that we will have 3 possibilities. 2 lone pairs in axial position, 2 lone pairs in equatorial position, and 1 lone pair in axial and 1 in equatorial position. So which of these 3 electron arrangement is the most stable one. Let's count how many LP-LP repulsion we have at 90 degrees, how many LP-BP repulsion we have again at 90 degrees, and if you want you can count also the bond pair repulsion at 90 degrees, but in general you don't need it because the first two are already enough to define the most stable electron arrangement. So let's see for the first structure. For the first structure we have lone pair repulsion at 90 degrees equals to 0, because the two lone pair are at 180 degrees far apart. For the second one we have again LP repulsion at 90 degrees, which is 0 because the two lone pair are at 120 degrees far apart, so it's more than 90 degrees. And for the third structure we have LP at 90 degrees equals to 1, because we have one repulsion between the lone pair in axial position, which is 90 degrees far apart, for the second lone pair in equatorial position. This means we have already a big repulsion in this last structure. This means this structure we can already rule out because it has the highest repulsion, which is absent in the other two structures we have there. So we can already rule out this third structure. So we have two structures left. In order to understand which one of these two is the most stable one, let's go to see the second to last most important repulsion in VSEPR model, which is the repulsion between lone pair and bond pair. And let's see how many lone pair bond pair repulsion at 90 degrees we have. For the first structure we will have 6 of them, and for the second structure we will have only 4 of them, because each electron on the equatorial position will repel at 90 degrees with the two bond electrons in the axial position. So as you can see, we have already the answer, because in the first structure we have 6 of this repulsion, whereas in the second one we have only 4. This means that our second structure is the most stable one. We can also go and check how many bond pair repulsion we have there, just because your professor can ask you. So let's do also that. The number of bond pair repulsion at 90 degrees for the first structure is 0, whereas the number of bond pair repulsion for the second structure is 2. So we have more bond pair repulsion in our second structure, but this is anyway not important, because in our second structure we have less bond pair lone pair repulsion. As I told you at the beginning of this video, lone pair bond pair repulsion are greater repulsion if compared with bond pair. So this means that even if we have some bond pair repulsion at 90 degrees, is not enough to make our second structure more unstable than the first one with more bond pair lone pair repulsion. So this is our most stable electron arrangement. Let's erase, as we usually do, the lone pair, and let's see what is left. What is left is the so-called T-shape molecular geometry. So ClF3 has the molecular geometry which is the T-shape with angles of 90 degrees between the bond pairs. So, with these rules, you can find the molecular geometry of your molecule. Just follow the flowchart I have given to you. You can find this flowchart and also the PDF of this lesson in the link you can find in the description box. For this video is everything, and I will left you with a table which will summarize all the cases you can encounter during your exercise. So just watch this table I'm giving to you, and you will be able to do all the exercise